if we had f of x equals b to the x, and f of x is really a y, so we just rewrote that as y equals b to the x in step 1. We switch the x and the y in step 2 to find the inverse of our exponential function. Then we get x equals b to the y, and then we usually then solve for y. But we can't solve for y in this equation because it's an exponent, and that's where logarithms came from. They came from inverses of exponentials, and that's why we have them. So it kind of gives you the history of log functions. And then I've defined a log function for you. This notation gives us a way to name the inverse. F of x equals b to the y. The inverse of an exponential function is a log function. The inverse function with base b is called the log function with base b. And then we're talking a little bit about the log definition of a log here. If x is greater than b, later on when we start solving equations, we'll come back to this definition. For x must be greater than 0, and b must be greater than 0, and b cannot equal 1, all in the definition of a log. Y equals log base b of x is equivalent to b to the y is equal x. Sometimes we work a problem in log form, sometimes we work it in exponential form, sometimes it doesn't matter which form we work it in, sometimes it can only be worked in log form, and we kind of go back and forth. So the first thing that I'm going to do is, this should be familiar to you, but if it's not, it's because we didn't spend a lot of time on it in Algebra 2. The first set of your homework problems are going to say, write each equation in its equivalent exponential form. So they're going to give it to you in a log form. Your base is always the little subscript, so your base is 5. Your exponent is the 2. Logs are always equal to exponents, so your base is 5, your exponent is 2, and that only leaves one term left, which is your x. So if we rewrote 2 equals log base 5 of x in exponential form, it would be 5 to the second equals x, or x equals 5 to the second. You're not solving here. They're just reminding you how you go from log to exponential form. We're just changing languages here. Example 2, the base is b, the exponent is 3, and b to the third would be equal to 64. So this would be a problem where I would probably want to turn them into exponential form to solve them. A little bit easier to solve, or at least think of it exponentially. And example 3, the base is 3, the exponent is x, and 3 to the x would equal 7. So they're just gradually walking you through how you can change a log form into exponential form, because sometimes one form is easier than the other. Sometimes we have to solve with logs, and so forth. So this is just the very, very, very beginning. Next slide says write each equation in equivalent log form. So now we're going to go the other way. So we're going to say log. What's our base in example 4? 12. So the little subscript will be your 12. The next number comes from what 12 squared is equal to. So that would be x. And then remember, logs are always equal to your exponent. Logs are always equal to your exponent. So example 4 would be log base 12 of x equals 2. Example 5 would be log base b of 8 is equal to 3. Example 6 would be log base e of 9 is equal to y. Okay, to me the base is easy. We know it's the subscript. The log is equal to the exponent, so the only other place that other number has to go is after the base. Alright, these next problems are the ones that usually pop up on the ACT, and for those people that haven't had Algebra 2 yet, or don't remember their Algebra 2, or haven't had Precal yet, these are the logs that pop up on the ACT. Now they're asking us to evaluate. So 2 is our base, and 16 is our answer. So we're looking for the exponent that we would raise 2 to get 16. So 2 to what power 16? 4. So they're asking you to evaluate log base 2 of 16. So we know the base is 2. We know the answer is 16, so we're looking for the power. You're supposed to be able to do these in your head. Example 8. 7 is the base and the answer is 1 over 49. What exponent can you raise 7 to that'll give you 1 over 49? Negative 2. So the negative flips your answer over. We know 7 squared is 49, so 7 to the negative 2 would be 1 over 49. Then they get a little bit harder as you go through here. Log base 25 of 5. So what exponent can you raise 25 to that would give you 5? 1/2, because what does 1/2 represent if it's an exponent? Square root. 25 to the 1/2 means the square root. 25 to the 1/3 means the cube root. All right, example 10. 2 to what power equals the 5th root of 2? 2 to what power equals the 5th root of 2? We'll slide this up. 1/5. Good.
Wait, how do you know that?
Okay, so you would think about the 5th root of 2 as being 2 to the 1/5. So it goes back to the square root. If you want to write the square root as an exponent, the exponent's 1/2. If you want to write the cube root of something as an exponent, it's 1/3. If you want to write the 4th root of something, the exponent is 1/4. So now this problem says 2, the base, 2 to what power is equal to 2 to the 1/5? 2 to what power is equal to 2 to the 1/5? And the answer is 1/5. 11 says 4 to what power is equal to 4 to the 6th? 6. 11 is kind of like, 12 is kind of like 11, except the log is up in the exponent. This is where we start to learn that if the bases are the same here, it's just like 11, but it's written different. If the bases are the same, they just cancel out and you just get whatever's left, which is 23. So this is just kind of the beginning of log to exponential, exponential to log, evaluating a few logs that aren't very hard. 13 says graph f of x equals 5 to the x, which is an exponential graph, and then graph g of x equals log base 5 of x, which is a log graph, so these should be inverses in the same rectangular coordinate. So f of x equals 5 to the x. Y'all did this yesterday or today. Make a little t-chart for this one. Let's just do -1, 0, and 1. I think we have the idea of what exponential graphs look like. When x is -1, what is y? One-fifth, or 0.2. When x is 0, what is y? 1. When x is 1, what is y? 5. Okay, so we're going to graph both of these on the same graph. Alright, when we graph g of x equals log base 5 of x, we're going to want to turn that into exponential form. Okay, it'll make it a little bit easier to graph if we turn it into exponential form. So what's the base of log base 5 of x? 5. What's the exponent? G of x, which is really like a y, and what's all that equal to? So this is where last year I asked you to compare these two equations that I have circled. F of x equals 5 to the x and 5 to the y equals x. They're inverses. Okay? Logs and exponentials are inverses. These two are inverses of each other because they're both in base 5. So when you can do a couple different things. Once you realize what you're doing here, you can just take the t-chart of f of x equals 5 to the x, and you can just swap the x's and the y's. So on your log graph, you're not going to have the point -1 1/5. You're going to have the point 1/5 -1. And then you won't have 0 1. You'll have 1 0. And then you won't have 1 5. You'll have 5 1. Okay? If you didn't realize they're inverses, then you would pick y's. You would pick -1 0 and 1 for your y values because your y is your exponent. And then you would plug your y's in to get your x. And then you might realize, oh, all these points are inverses. And then you're going to graph those 3 points. Log functions have vertical lines that are asymptotes. Log functions have vertical lines that are asymptotes. Exponential functions have horizontal lines that are asymptotes. So when we graph the log function, it's not going to approach a horizontal line, it's going to approach a vertical line. So we're going to graph 1/5 -1, which is kind of hard to graph. I'm not going to graph that. I'm just going to pretend that it's there. And then 5 1. And in that big, long, ugly definition, it says that an exponential and its inverse are reflections over the line y equals x. So if I draw in the line y equals x, you can see visually how the blue line, if you reflect it over the green line, if I were on graph paper, you would get, if you folded over that line of reflection, you would get the same graphs. Because a graph and its inverse are always reflections over the line y equals x. So we'll start to study log functions a little bit more. And a lot of people that's kind of when y'all probably just lost track in Algebra 2 is when we actually started graphing the log functions, because that was really, really new to you, and this will give you a little extra chance to see those again. So log functions are going to approach vertical asymptotes, and exponential functions are always going to approach horizontal asymptotes. That's because their x's and their y's have swapped. Everything about them, everything about the x turns into the y, everything about the y turns into the x. That's why their asymptotes are different. All right, was that the last example? Okay. All right, if y'all will just spread out just a little bit from your group.